We're very pleased to welcome today Yvonne Gao to talk with us about her recent experiments and her, I guess, planned experiments as well. Yvonne did her PhD in the very prestigious Yale Superconducting Qubits group and has won a very prestigious fellowship to start up her own group now at the National University of Singapore. And she's going to talk to us about her work with Bosonic Qubits, and very excited to hear all the latest news. Take it away, Yvonne. Thanks very much.
Thank you, Nathan, for the introduction. And hi, everyone. So I noticed that the previous talks in the seminar so far has mostly been theory talks. So we're going to switch gears a little bit, and we're going to focus a lot more on the hardware and experimental aspects of actually doing quantum information processing with bosonic qubits in a circuit QED architecture. Okay, so I think to start with, I just want to maybe summarize a little bit about what's going on in the experimental domain for building quantum computers these days. So I found this really nice little chart from one of the recent review papers from Will Oliver and a couple other people. So one way to think about the current status is that, we've been working very consistently on improving the basic building blocks for circuit QED quantum computing systems. So that goes from just building more and more robust qubits to having better control lines, control electronics, doing better readouts and better gates. Right, so these are the necessary parts that have been, that's been constantly improving over the past decade. And as we're getting better with these, we are starting to explore the next step in using these systems to actually do something interesting and move further along the lines of building a quantum computer. So I think this is where it starts to diverge a little bit. So one path is maybe the NISQ approach, the NISQ efforts, where groups are focusing on using what we already have to piece them together and make prototypical quantum processors that can maybe start to implement some interesting quantum tasks or even achieve a little bit of an advantage over our classical computing systems. So there's a lot of recent developments in this area, quantum supremacy, whatnot. So this is clearly a very interesting field, but there are some challenges in this approach because once we're in this NISQ era, we'll have to eventually look into the challenge of quantum error correction to ensure that the computation will eventually be faithful and robust enough to solve real problems. Right, so while the sort of prototypical processors are extremely useful for us to learn about scaling up the system and how they behave, what their failure modes are, I think it's also important that we tackle the challenges in parallel in a slightly different manner. Right, and this brings me to the approach that some of us are working on at Yale, Chicago, and a few other big research centers all over the world. And this you can imagine as being something that first focuses on quantum error correction and then scaling up, right? So I think the efforts started with groups of people working on how to encode the information in a protected way, but without the large amount of overhead that, say, a surface code would require. And I think this, brought in a whole host of interesting new encoding schemes. And I think the leading platform right now in this arena is Bosonic Qubits encoded in superconducting cavities. Right, I will talk about the details of that a little bit later. But in general, I think the outlook for this alternative path or this parallel effort is that we want to first figure out ways to do error correction on a single mode to make sure that we can have protected qubits that can live longer than its physical elements. And then we want to move into the areas of actually doing operations or multi-qubit gates on these protected systems, and eventually scaling them up and putting more of them together to have the complexity and the performance requirement needed to actually build a fault-tolerant and general purpose quantum computer. Right? And this is the approach that I will focus on. And in general, I think the way we think about bosonic encoding, which I've alluded to earlier, is that it offers some very important advantages that actually makes the task of quantum error correction more tractable, right? And the rationale is really quite intuitive. So in general, I think the more textbook approach to encoding information redundantly to offer protection against quantum noise is to use a collection of two-level systems. So these could be, spins or transmons or fluxoniums or what have you not. But in general, for each two-level system, we can have a few different ways, different error channels, and that includes spontaneous emission, sometimes thermal population jumping upwards, as well as dephasing and other things. And if we put more of these together, we see that with every mode we add, we actually end up adding additional noise channels. And more importantly, as we put them together, we actually introduce some errors that are somewhat uncorrectable, and this could be long-range connections or interactions that are not controllable. So generally, we call these crosstalks. So you can imagine the neighbors could have a coupling that's always on, and that's something that we do not want. Even worse, we could imagine if there's some sort of mode overlap in the spectral domain, then we could have even longer range interactions that could really mess up our computation, right? So this approach in general gives us a very quick scaling of the Hilbert space that we want to have for quantum error correction. But the trade-off is that we are adding more failure modes and introducing some potentially uncorrectable errors. And in general, controlling all of these modes individually and doing gates among them is quite a challenging task. I mean, there's a lot of remarkable engineering achievements in this area, but it's still a relatively challenging task to achieve, right? So one way we thought about approaching this is to think about these challenges and see what platform could give us a easier time to actually achieve this large Hilbert space for encoding the information without adding all these bad things to it. And that's where we arrived at using harmonic modes. And it's quite clear that when we have a harmonic mode, we can use a lot of these different levels. And we can, once we couple this to any sort of nonlinear ancilla, we then can control these levels individually and break the degeneracy. So that's really convenient. But the more important part is that despite having access to a much larger Hilbert space, we now still only have a single dominant error channel, right? That's just the way, that's simply just a harmonic oscillator losing its energy. The dephasing is typically quite minimal. So there are some minor error channels, but the dominant way of losing information or having a quantum error occurring is due to photon loss. And the fact that there's only one channel makes the concept of tracking the errors and correcting them a lot more tractable, and also reduces the hardware overhead that we need to put together in order to achieve this large Hilbert space, right? Because the control we need is still a single mode control. We can address all of these excitations in whatever combinations, just using clever tricks with one single cavity and one nonlinear ancilla, right? So in general, I think the bosonic encoding, compared to the traditional way of putting information in a collection of two-level systems, offers quite a lot of interesting and useful advantages. And that's why there's been quite a lot of efforts in this area, both in the theory and experimental areas in the recent years. Okay, so just to summarize, I think looking into this little outlook, we have indeed realized quite a lot of different encodings of logical qubits in this type of bosonic encoding schemes. And here are just a few examples. They're somewhat recent. Some of them are actually fresh out of the experimental lab. So we have the GKP code, the Bosonic code, and CAD code as the three leading contenders for being the choice of encoding. But there are more being developed, both in theory and experiments, just as we're going further in this area. So once we have created these interesting encoding schemes, we also looked into how to do single qubit operations on them, right? If we can only store them as quantum memories and not have any way of interacting with them, then they're essentially not that useful for quantum information processing. And in terms of doing operations, there are also a lot of different approaches. But so far, I think there's been several demonstrations of implementing universal control with relatively good fidelity on all of these encoding schemes, right? So that's really exciting. And I think we're ready to now, tackle the next step while still making improvements on these preliminary building blocks. And the next step, the logical next step, is really starting to look into multi-qubit gates on these encoded bosonic systems. And there has been some work in this area already. So in 2018, one of my group mates at Yale and we actually worked on making a CNOT gate between two of these qubits. But they are, these two examples so far, they are very much dependent on the choice of encoding. So what that means is that we choose a particular way of encoding information in our bosonic modes, and we engineer a specific gate just tailored for that particular choice of encoding. And that has quite a lot of limitations, right? So I think to go forward into building a general purpose quantum computer, what we really want to achieve, is that we want to make gates that are generally code word independent. These check marks are not supposed to be there yet, and they should be programmable. So we want to be able to, turn them on and off well, but also maybe change them during the computation to implement a different type of gate on our protected qubits. And we also want to make sure that whatever we engineer eventually will form a complete gate set so that we can have universal control and really implement any algorithm that we want to on these systems. So here, what I'm aiming to illustrate is really that when we have the simplest architecture we can imagine is to have two bosonic codes, and we want to be able to choose whatever encoding we need for their particular local error model or their particular functionality, and still implement our gates on them without having to change the hardware, right? So in this talk, I'll basically introduce to you some of our recent results on two of these interactions. One is a driven bilinear coupling, and this can be used to realize beam splitters or swap gates between two cavity modes or bosonic modes. And then I'll talk about how we build upon this bilinear coupling to actually make a universal entangling gate for bosonic qubits. Okay, but before we go into the details of these two operations, let's just have a look at the hardware, right? So it generally looks something like this when we have two cavities. From the side view, so this is just a piece of bulk high purity aluminum, and we machine it to have the structure, the desired structures and the connectivity ports built in. So each one of these is a 3D microwave cavity. From the side view, looks something like this, where we have a cylindrical cavity with a stub in the middle that defines the exact mode structure and the frequency of its modes. These cavities are generally designed to have the aspect ratio such that there's a good protection against leakage, the electric field leaking out of the cavities. So there's protection from loss due to that. We also have a nonlinear ancilla inserted into the tunnel design here. So this chip corresponds to this chip here. And this is just a standard single junction transmon qubit. So there's a standard Josephson junction with some large capacitance pads. And the reason why it looks like this is because we want to have a simultaneous dispersive coupling to both of the cavities. And this is actually a really flexible way of designing it. If we were to have more cavities, it is completely adaptable to introduce additional capacitive coupling structures, which is quite nice. On the same chip, we also have a strip of metal. And this is actually a really neat design, came up by someone at Yale, that, with this simple structure, together with the walls, the metal walls of the tunnel, it actually forms a strip line resonator. So what this gives us is a very simple and cheap way of getting another mode onto the same chip, where we can use for fast readout or the reset of the transmon mode. Okay, so with this simple architecture, we can actually have control over both, universal control over both Alice and Bob, which are our two bosonic qubits. We also have generally really good isolation between these two, because the fact that they are spectrally separated and also housed in distinct cavity structures makes them have very, very little mode overlap. So I think the, natural or always on coupling between these two cavities is only mediated through this nonlinear ancilla, and it's higher order in their coupling strength. So it's really a small effect, I think, on the order of kilohertz. It's very hard to measure, actually. So that's nice, because now we have two distinct bosonic qubits that do not have any unwanted always-on couplings between them. And finally, this is quite a flexible architecture as well, because we can introduce additional ancilla or additional readout modes to each of these cavities, or even further if we wish to reconfigure the system to provide a little bit more control capabilities or additional gate capacities. Okay, so looking into this architecture, as I was saying, these two cavities are well isolated, and generally they're, the fact that they are largely detuned by close to a gigahertz usually means that if we have something here and something in Bob, they will not mix with each other naturally, or there will be no operation or gates possible without intentionally engineering something. And the task, so with this architecture, actually, the first thing we did is to just see if we can actually initialize states in the two of them. And that's been done and seems to be a relatively straightforward task. So the next thing we wanted to do is to see, can we now intentionally engineer a coupling between them, right? So that now we can have useful gates between two well-isolated and potentially protected bosonic qubits. And this is something that we can draw inspiration from old works in the group and many others in this field, which is basically the amplifier processes, right? They actually make use of the four-wave mixing abilities of the Josephson junction to achieve parametric conversion or amplification. And in our system, it's actually not that different. We have two modes that are detuned. They don't talk to each other naturally, but we want to drive, if we drive it in a certain way, maybe we can enact a frequency converting interaction, right? So the thinking process is really, now let's use this junction not just as a nonlinear ancilla, we actually wanted to use it as a converter. So the idea is that if we choose the drive such that the detuning between the drives exactly compensates the energy difference between the two cavities, then we should be able to actually achieve a bilinear coupling that looks like this, right? So basically you can take one excitation from Alice and put in Bob and vice versa. And this is a time dependent one, and basically depends on the duration and the amplitude of the drives that we choose. So it's a very much tunable process based on how we drive the system. And intuitively, this is also easy to characterize, right? So if we just initialize Alice with one single excitation and we turn on this coupling, the signature of this actually successfully working is that the single oscillation should basically go back and forth between Alice and Bob without losing its coherence. And this is the first experiment that we did to see if we've managed to achieve this process. And this is just a simple measurement of a joint probability of one excitation in Alice and 0 in Bob. And what we see is that it oscillates periodically over hundreds of microseconds. And what's important to note that is that now we want to see when it's no longer in Alice, it is indeed in Bob. It's not somewhere lost somewhere else, or starts to go into a different leakage mode, right? So we did the reciprocal measurement of measuring the probability of that excitation being Bob and nothing left in Alice. And we see that the oscillation is basically exactly out of phase with roughly the same decay envelope. And this is, very consistent with our expectations. So in general, I think we conclude that if we drive it with a chosen set of amplitude, we can find a pulse duration that gives us a full swap, where the excitation is taken out of Alice and completely transferred to Bob. And if we stop halfway, we can have a process that's essentially a balanced beam splitter between the two modes. Okay, so this is a good indication of the fact that we can drive a coherent coupling between the two modes, even though they are not naturally coupled to each other. Okay, so after this sort of initial tests, the next natural thing for us to do is to actually check that we can now transfer not only a single photon, but something that has a phase property as well. So what we tried to do is that we initialize Alice in vacuum, but Bob in a superposition state, right? So this is usually a useful test for anything involving quantum transfer or quantum gates, is to make sure that we don't only move the excitation, but we also maintain the phase coherence during the process. What we did is to turn on the swap coupling, or two beam splitter durations, and we measured the Wigner function of the final output state from Alice and Bob individually, and we see that the state is fully transferred to Alice, and Bob now is completely evacuated, right? So this also gives us the reassurance that our process preserves the phase coherence of the quantum states we put into the cavities. And it can, this also provides the confidence that this will be basically compatible with any sort of quantum state we put in these cavities. They can be the protected, they can be the error correctable cat states or boson or GKP states, and our operation will still be useful as a swap gate. Right. So this is something very useful, but still at this point, everything about the operation is essentially linear still. Right, and I think we all know that to do useful quantum information processing, we will have to eventually have an entangling operation one way or another. And what we wanted to see is that, with our beam splitter coupling, does that give us a good entangling operation? Because it is possible to entangle states using a beam splitter, right? So as part of that verification, what we did is to see how the statistics evolve as a function of the evolution under the beam splitter coupling between the two cavities. And the setup is something like this, where we initialize both of the cavities in their single photon Fock states. And we turn on our coupling and basically observe the statistics at each of the cavities after each duration of the beam splitter. What we see is that what we observe in the z-axis here is the probability of measuring a particular distribution of the combination of photons. And we see is that in the beginning, we have the 1-1 state being the most likely, which is consistent because that's our initial state. And as we turn on this coupling, we see that we oscillate out of the 1-1 states completely and go into an equal superposition of the 0-2 and 2-0 states, right? So this is very much the frequency converting version of the classic Hong-Ou-Mandel interference experiment. And at the next cycle, we actually refocus back to 1-1. And then it coherently oscillates back and forth between these two possible subspace as we go along. But what we observe here is that, there is indeed an entangled state at the end is the null state, but we have leaked out of our encoding space, right? So our initial code space is in 0, 1, but now we've gone into a space where it's 0, 2, or 2, 0, and this is actually not good for quantum error correction and using protected and using bosonic encodings to do information processing. So, from here, I think what it's important to recognize is that a beam splitter doesn't in itself generate entanglement. The entanglement is really due to the fact that we're putting in a highly non-classical state, right? So just to completely put that, verify that, we then try a different type of initial state, which is semi-classical. It's just a standard coherent state and the vacuum state. And if we do the same process, we realize that at the end of it, we actually do not get any entangled state. We just get two coherent states of half of the amplitude of the initial input coherent state. So what this tells us is that a single beam splitter doesn't give us a good entangling gate for general purpose quantum information processing. It always brings us out of our original code space, which is not desirable as well. So this motivates us to build upon this and actually go further to build a code independent entangling operation. So how do we generally approach this task of making entangling gate, right? In general, I think my intuition is that if we can achieve a superposition of doing a swap gate and not doing a swap gate, which is identity, then we can actually entangling the two modes that's involved in this operation. So this actually can be translated into this eSWAP operation. It's been proposed by Lau and Planu a few years ago in a theory proposal, but in general, it really is just a tunable superposition of the identity and the swap. And the coefficient in front is controlled by a rotation angle introduced to the system by an ancilla. Okay, so this is actually a very useful gate because it is compatible with any bosonic platforms because neither of these operations are dependent on the choice of code words. It actually also provides the missing entangling gate to form a universal gate set. So with this, plus just single mode control, we can have a complete gate set to implement any algorithms. And finally, it also has other uses outside just forming a complete gate set for universal control. There are other applications as well. So that's why I think once we had the swap operation, this was the next thing on our agenda because it's a really useful operation to be able to have in our repertoire for bosonic encodings. So physically, how do we implement this? Is that we constructed out of two beam splitters separated by two controlled phase shifts plus single mode rotations. So there's more details about why we chose this specific implementation in Liang Jiang and Steve Gervin's paper. But the general rationale or intuition is that we want the ancilla, which usually is provided by the nonlinearity of a transmon, and it tends to be the least coherent element in a system like this. The cavities have coherence up to milliseconds, and the transmons are usually tens of microseconds in coherence. So generally, we want to keep the transmon or the ancilla in the ground state as much as possible. So in this case, we actually managed to make it start in ground state and end in ground state. So it's only actively involved in the system over a short duration. Also, for the control phase gates, we actually have a very natural way of implementing this because this is essentially just measuring the parity or what we use to map out the parity of the cavity using the natural dispersive interaction between the ancilla and these bosonic modes. And finally, the overall gate time is not very long compared to the coherence of the two cavities. And everything in here is purely microwave activated. So there's no special hardware that we need to build in, such as new flux drive lines and things like that. So we can program this on demand if such a gate is needed. And we can turn it off completely when the computation is in idle times or other operations are in process. Okay, so with this circuit in mind, and all these building blocks that's already available to us, we realized we implemented this protocol, and as a test, we looked into, putting in the system our semi-classical states again. So this is the state where no entanglement is achieved if we only have a single beam splitter. But now we put in our eSWAP circuit, and we should expect to see a fully entangled two-mode state, where you can see that there's there's full correlation between the phases of each of the coherent state components in the system. And this process is deterministic. It does preserve the code space, and overall, it also preserves the joint parity, which can be used as a error syndrome for monitoring whether we've had a photon jam event in either of the cavities or not, right? So this is what we expect to see. And in terms of its experimental signatures, what we should observe if we measure the joint Wigner function, and this may not be the most intuitive, so I'll try to go through this a little bit slower. So what I'm showing here is the simulated 4-mode Wigner tomography, but a plane cut in that 4D phase space, right? So here in the top graph, I'm showing the imaginary and the imaginary planes. And what we see is just interference patterns or the fringes, which is a good indication of quantum coherence. And in the real plane, we see that we observe the distribution of the population, right? Because you see, we started with alpha and minus alpha. At the end of it, if our gate is really preserving the excitation and the joint parity, then we should see that the probability of measuring any population in the system should still be focused on alpha and minus alpha. Okay, so these two planes actually give us a good indication of whether we've managed to make a 2-mode entangled state with our operation. The full characterization of the state will require us to have more statistics in different points in the 4D phase space, but these two snapshots actually provide a good intuitive picture of whether that's been achieved or not. What we measure actually is something that looks very similar. In the imaginary and imaginary plane, we see the coherent oscillations. And in the real plane, we see the population distribution at the correct place. And you can see that there is a little bit of additional feature in the middle, and it looks coherent, right? This is not just noise, it actually has a feature. And this led us to think about what additional higher order effects could be happening. And we actually managed to pin it down to the higher order nonlinearities in the two bosonic qubits inherited from the nonlinear ancilla. So this is sometimes called the kerr, the self-kerr of the cavity. So if we put that if we independently measure that and put that into our simulation, then we actually reproduce this small feature in the center of the Wigner cut quite precisely. So, so I think this is a good indication that we've indeed achieved such a state. With this in mind, we can also characterize it in the logical subspace, which is basically mapping alpha to 0, logical 0, minus alpha to 1, for example, and see that how well we can actually achieve a 2-qubit gate in this exact encoding, right? And this is a standard Pauli measurement of two modes. And we see that all the expectation values are indeed at where they should be. The slightly transparent bars are the simulated values, and the fully colored ones are what we measured. So just raw numbers extracted from our state tomography experiments. So there are a little bit of spurious distribution, and we can account for these by taking into account of the higher order nonlinearity in our system. So this provides a good indication that we can use our eSWAP gate as a 2-qubit entangling operation. And it does preserve our code space well. All right, so far, I think based on what I've shown you, we could extract the raw quality of our operation. So here you can see that 74% is actually not that impressive, but this is without any correction of measurements or state preparation. So we could identify where most of the missing fidelities are. A majority of them actually come from spam errors. And this is because measuring the joint Wigner function at the moment is still not extremely efficient. So it takes a little bit longer, leading to potentially more errors in the measurement process and a reduced contrast as a result of that. The next big effect, accounting for several percent, up to 5, is the Kerr nonlinearity inherited from its from the nonlinear ancilla we introduced to the system. And then we have a little bit of the decoherence effects as well as nonlinearities in our operation. But overall, I think this gate has the potential to be improved quite a lot more to the 90–95% level by simply accounting for the spam aspects of the system. Okay, and you know, just to conclude also for this particular gate, so far I've only shown you one particular angle in this operation, which is the fully entangling case. But if we really engineered a full unitary operation with the possibility of tuning it, then we should be able to observe, we should be able to do a controlled rotation and basically observe its full evolution from a simple identity gate to an entangling gate and then back to a swap gate, right? So with this, what we could do is to sweep the rotation angle while monitoring some of the key elements in the 2-qubit Pauli operators. For the II and ZZ component, for example, what we observe is that they stay constant, and this makes sense because they represent the population, so the excitations in the system, as well as the parity in the system. So they should not be varying as a function of this angle. But if we look at the distribution of the IZ and ZI components, we see coherent oscillations. So this corresponds to it moving from fully an identity gate to a swap gate. And if we look at the 2-qubit joint correlated operators, we actually see out of phase oscillations that are of the same amplitude and the same period. Right. So now we actually have a much clearer picture of how the entire unitary operates as a function of our tunable or programmable rotation angle. And the final characterization process we did is full process tomography. And without going too much into details of this, I just want to show that we are able to do joint tomography of 2 bosonic qubits, even though, you know, it's a large joint Hilbert space. This is a little bit resource intensive, but it's something that we have the techniques to do. And we can compare the resulting state process tomography data with the expected one, and we see that we generally reproduce all the crucial features with some additional spurious distributions, which we can map onto the error or the imperfections that we've identified before. Okay, so in general, we do have a very complete set of tools to both initialize states, implement an operation, and then do full tomography to characterize the operation in an architecture like this. So we also tried this on several different encodings. So the two quoted here are the the Fock state encoding and the binomial state encoding. Again, all of these are limited by spam errors, And you know, these numbers, if we normalize out the readout as well as the state preparation, we are actually in the 90% range for both encoding. So this actually concludes the talk about these two particular operations we've engineered between two bosonic systems. And as promised, I think our data does show that, you know, these operations are generally code independent. We can program them, we can switch them on and off, and we can use them to do universal manipulations on the bosonic qubits. So what's, you know, since this has been done, a lot has happened at Yale and elsewhere as well. So just a little bit of outlook actually. Following these efforts, people have started to build more and more powerful quantum modules using similar architectures. So this is our first generation. It's, you know, we think of it as maybe the first kind of transistor type of thing. It's bulky. It doesn't have many modes. It's, you know, it's useful as a test bed, but maybe not super useful as a information processing module yet. But fairly quickly, within a year or two, people at Yale, other groups at Yale are actually starting to build larger devices with similar design philosophies. For example, this particular device has 4 bosonic qubits and 4 nonlinear ancillas. And the team have managed to use it to implement a teleported gate between 2 of these chosen bosonic qubits. So there's a lot of interesting and exciting work going on in this architecture. And just in terms of, you know, the fact that the footprint of these are so big, and maybe it beckons the question of how do we keep building larger and larger things with this device. There are some alternatives that still retains the main design considerations of this architecture, but reducing its footprint. And this is something developed at Yale and Lincoln Labs and a few other places. That's called the multi-layer micro-machined quantum system, where you can see that the cavities now can be etched on a silicon wafer, so its footprint is much smaller, and we can use these stacked multi-layer structure to introduce the ancilla, the control lines in a much more compact manner. So, so I think there's, you know, a lot of excitement in this architecture as well at the moment, because once the design and the optimization process of this is complete, then we can start to realize some of these devices in a more compact form and maybe with more flexible control capabilities as well. What's also interesting is that since the experiments we did at Yale was finished, another team actually took over the same device. So this is exactly the same device we used and adapted it into a bosonic simulator, right? So it has the same structure, 2 bosonic modes with a nonlinear mode in the middle, as well as 2 additional nonlinear ancilla. Its coherence is sort of reasonable. It's not state of the art, but it works well. And with this, they're actually able to run an interesting simulation about the vibronic structure of a molecule given a certain electronic transition, right? So this is actually something that contains information about you know, the relative potential energy landscape between the vibrational states and the electronic states. And it's really useful for quantum chemistry processes in general. What's remarkable is that this is actually a really hard process to simulate if we were using the 2-level based approach, because this is a bosonic system and we have to coerce all the 2-level devices to behave as bosons in order to actually emulate this process. But with our bosonic cavities, we actually have a very natural and efficient way to simulate this process. It's just using 2 cavities and 2 to 3 nonlinear ancilla. And what they observed, the main result is really that you know, in the small system, we can still fully simulate the structure. These are the solid black lines. And the calculated one using our bosonic system is actually a very good very good reproduction of the features that we want to observe, the signatures of the vibronic transitions. So this is a very interesting result, and actually another really highlights another benefit of using structures like this is that it's very versatile. So you can change the design parameters slightly and use it for a completely different type of operation. And more details of this paper can be found on the archive, or you should be coming out on PRX in like a week or two. Okay, so this is another aspect that I'm pretty excited about as well. So just to wrap up, I think overall in this talk, I showed two types of programmable interactions between these bosonic modes stored in superconducting cavities. They are useful for doing, code and agnostic computation using bosonic qubits. They're also useful for things like just studying interesting interference effects, etc. So there are more details in these two publications. And we do see that, our current mode of operation is useful, but maybe not perfect yet. So there are many potential ways to improve that just using slightly different mixing elements. So the single Josephson junction case is the easiest way to do this, but with a bit of engineering, we can actually have more adapted mixing elements. And this is being explored in a few different groups at the moment. And finally, I think our architecture is pretty promising in a sense that it can be extended to higher modes. It can be used for other computational, implementation of computational tasks or higher order encodings, for example, as sort of a repetition code of some sort with each of the subsystems already a protected bosonic qubit. Or maybe with more modes, we can also have some sort of primitive surface code where each of the individual element is actually a bosonic qubit rather than just a simple two-level system. So this potentially would have the effect of reducing the overhead we need for surface code. And finally, I've also shown this little snapshot of a simulation experiment using using basically the same architecture and the same device. And that also opens up a whole host of other possibilities for adapting this to study interesting effects in chemistry and condensed matter physics. So with that, I would like to thank you for joining us on this talk. It's been, a great experience so far setting up my group. We're still very young, so we have lots of postdoc and PhD positions available. And if you're interested, so you can check out our website or just reach out to me. I'll be happy to have a chat or share with you more about our work, our future work, and the team. Thank you.
All right, fantastic. Thanks very much, Yvonne. I'm going to simulate the applause that's coming from all over the different place, I'm sure. Now I would like to open up to questions from the audience. If anyone has them, just unmute yourself and say hello, and we'll get going.
Hey. I have a question
Go ahead.
about the tomography.
Mm-hmm.
The difference between the Wigner tomography and then kind of like the subspace tomography, do you find that when you're doing the Wigner tomography,
Yeah.
I mean, it's a bit overcomplete, right?
Yeah.
Or perhaps very overcomplete. Do you find that gives you like additional insights and information to see these pictures?
That's a really good question. I think the honest answer is that these pictures are not really necessary, but they're very pretty. So so we just take them as a sort of a presentation tool because they offer a bit of intuition with the features. What we actually do to or what we use to actually do the full tomography is that we sample the phase space in using random displacements. So we actually sample a minimal requirement of points that will give us a complete complete state tomography. And we just do that randomly across different points in phase space to make it as non-biased as possible. So
does the
answer,
randomness come
yeah,
from like a compressed sensing kind of?
It's a condensed version. It's a simplified version of condensed sensing. So we run it numerically first to see if we, we optimize the displacements a little bit to say which set of random displacements will give us the best condition number, or with the inversion and all that, and then we implement that in the actual tomography process.
So just following up on that, does that mean that the Wigner tomographies are not directly measured tomographies, but reconstructed from these full density matrices that you get out of this compressed sensing tomography?
So these Wigner snapshots, they are directly measured. So these are actually just raw data, but we can't afford to do this sort of dense sampling for every plane in the 4D space. So what we do to construct the full density matrix is to do the compressed sensing approach. But we do have a few directly measured snapshots like this, for example, where we can actually look at it and have a bit of intuition and see that, we're doing the right thing and we have all the right features.
Ben, did you have a question?
Yeah, I was just gonna ask generally about, so like, over the past, 10 years or so, there's been loads and loads of experimental progress on control of single cavities.
Yep.
And, just like last year, we have GKP states and binomial codes and lots of cool stuff going on.
Yep.
And what you talked about is coupling of two, controlled cavities.
Yes.
And is there a whole lot of other work going on, like other groups? I mean, this is the next step, right? If you're going to use this for quantum computation, let's say, you do a really good job in a single system, but now we're going to have to start putting them together. So I was just going to ask more about like the general overview of what's going on in two modes or more.
Yeah, great. Yeah, I totally agree that this is really the natural next step. And I think, right now, the works that I'm aware of is that, there's, I think Yale might be currently leading this effort on doing multimode stuff with these protected qubits. And I think they are, so for example, Dave Schuster's group in Chicago, they're making these multi-mode cavities. So this quantum flute structure, for example, where they can implement similar things in a maybe slightly different design. So there are quite a lot of efforts just starting to tackle this question of how do we put more of these together and do interesting operations among them. But I think that, more and more of the bits and pieces are becoming available for us to use. So I do think that we'll see more publications and results in this area in the next year or two.
Are you planning to continue in this direction?
Yes. So for me, I think for my new group, one thing we'll focus on is to look into, going beyond just two modes. We may need a bit of architecture change. So we have some designs in mind where that will allow us to have more sort of an easier time to have more bosonic modes and nonlinear modes interacting with each other. So that's one thing that we'll definitely pursue. And maybe not so much on, maybe not so much on doing algorithms on these bosonic qubits, but more on building the tools that will enable that. So for example, for now, we have ways to connect two bosonic qubits that are in separate modules, right? So there's a recent, not quite recent anymore, I think 2019, it came out in Nature Physics. This is the pitch and catch experiment where they can send the bosonic qubit from one side of one module to another. But a lot of these efforts, so this can be a single photon state or a error correctable state, in different ways, but all of these experiments so far are sort of one-to-one. So another thing we're thinking about is, can we have some sort of equivalent of a router so that you could really pitch your bosonic qubit from one mode to another on the fly, or one mode to many other modes on the fly. So these are some of the directions we're looking into that will, I guess, provide the building blocks for doing full algorithms on these qubits.
Right. Cool.
Josh, I saw you unmuted yourself momentarily. Do you have a question?
Hi, Yvonne, how are you?
Good.
I was more or less going to ask Ben's question with a slightly different spin, perhaps, which was, it seems at least that going from a single system and coupling two systems is a big experimental challenge. But what's like the next hurdle? And I think you've kind of given a partial answer to that. So, yeah, that was great.
Thank you. Yeah, I think one, just to follow up, maybe more of as a comment to that, is that, personally, I think as a new group, we have some ideas for the moment, but what I really wish to see, and I think, some of the Yale people or the more established groups are already working on, is really looking into the next step of higher level encodings. So Maziar had a paper out in PRX, I think late last year, about maybe repetition code with CAD qubits, or people are really thinking about small surface code with GKPs and things like that, which I would be very much excited to see taking place experimentally soon.
Okay. Yeah. I mean, okay. So that is a good answer. I think that concatenation with another code would be a big step forward as well.
Exactly. Yes.
Yeah.
Yep.
Yeah. Cool. Thank you.
Well, I actually have a question. I have lots of questions actually, but one in particular, again, about the tomography.
Yep.
When you were doing these these Pauli basis tomographies, for example, in the bosonic mode space.
Yep.
Obviously, there's an issue with these continuous variable encodings that the qubit space is only a subspace of the overall Hilbert space. These tomographies here, are they kind of renormalized to only include the qubit space, or how much probability do you lose to being outside this kind of 2-qubit Pauli basis?
Yeah, that's a really good question, actually. So I guess to start with, the data here is not normalized. So I think what we see losing is actually part of it is really from leakage. So for example, Kerr would cause that leakage as well. So I don't have a quantitative analysis of this at this point, but I think so I remember us trying to figure this out just intuitively a little bit. What we try to do is to actually trying to do this in different ways to compare whether the way we're doing it is biased, against leakage, or favoring, counting leakage as non-errors or not. So for this particular set of data, we actually did it by directly measuring certain points in phase space. So there's no reconstruction. And then for other sets of data with a similar goal in mind, we did full density matrix, and then we extract the 2-qubit operators, and then we check them against our direct measurements. And we actually see that they are fairly consistent. So that doesn't mean that we're accounting for leakage correctly. That most likely means that we're dominated by STEM at this point, so that the deviation due to leakage is something that's a little bit masked at this in these data sets. So we don't have a good knob on quantitatively putting a number on it.
Yep. Okay. That's very interesting. And my second question, which is a little bit related to that, I guess, well, maybe because the way you were talking about spam errors, one of your early plots where you were testing the SWAP capabilities of, this one.
Yep.
So you have an initial probability here of 0.8. So
yes.
But actually with the coherence times in those cavities, often like previous experiments that have been optimized for this have obviously been able to create very, very high probabilities of single photon states. So what's the limitation here?
That's a really good question. I think we get asked this every time, but we still show this data just to show that our honesty about it. So this is really purely due to the detection problem. So and it's really a result of how we measured it, not an inherent problem. So the way we measure this is is to measure joint probability, not single probabilities. So what we did is actually we do two readouts, and we do correlations to figure out joint probabilities. So we suffer from both of the readouts. Another thing is that because this is a single photon state, we're measuring not the parity, which is much higher quality. We're actually using a very selective pulse to measure the photon number, number splitting peaks to ensure that we're really in 0, 1, but not, a bit of 2 and things like that. So it's a very long and selective pulse, and that's actually lowering the quality of the detection quite a bit.
Right.
So as a result of that, we see that the overall scale is reduced, but the fact that it's consistent across the two measurements, and the decaying envelope is slow, tells us that this is really a detection problem, not a coherence of the operation problem.
Right. Okay.
But this is a problem. Yeah.
Yeah, go on. Sorry.
I was just going to say that, this is something that we can completely get around by doing a different method of detection for this joint probability.
Right. And did you say that this swap operation then works completely well, like it works as well for an arbitrary state? I didn't quite catch that.
What we tried a variety of different input states. We see that, so for example, for this, we're only doing single mode parity measurements at the end, and we're only initializing a single cavity state, a smallish cavity state. So the spam is not as high, and you can see the contrast is very good. We tried the same with different states, and what we observe is that as the states gets more complex, we see an overall reduction in the contrast, but that's mostly due to the difficulty in preparing a very large cat state or a very large binomial state. The diminished contrast after the operation between the various inputs are basically the same. So it's about 2% loss due to the actual swap.
Because I guess somehow I would think that if you just put a 2-photon state onto a beam splitter, my intuition, and I've not done the full calculation, I guess, for this situation, but my intuition is that you would actually get some complicated, some complicated superposition of different photon number states, and you wouldn't necessarily get a complete swap over to the other mode for arbitrary photon number. But I don't know whether that's, but I don't know whether this, I mean, this is a bit different from maybe the situation that I'm familiar with. So I'm not sure whether my intuition is holding correctly.
So I think I see what you mean. The reason why this swap operation shouldn't and doesn't seem to care about the input state is that, the strength, the rate of the swap scales with the photon number as well. So overall, we can achieve a full swap no matter what the input state is. So with 1 photon, you will go at a particular rate, right? But now if you have 2 photons, you have the higher photons present. They will go like 1 by 1, but at a faster rate.
Right. Okay.
So overall, we actually achieve a swap, with all the different photon distributions. With larger photon numbers, there is a little bit of a concern about dephasing, because now there are more and more peaks that needs to refocus back exactly right. So the higher order Kerr effects and dephasing could come into play, but we never explored, like more than, say, a cutoff of 15 photons or something. So generally, there are still relatively small states.
Okay.
So
well, maybe that's something that we can discuss a bit further offline. Are there any other questions from the audience before we wrap up?
Yeah, I put a question in the chat while you were talking. This is Ben again.
Yeah, hi.
Hey, no, I was just wondering about the fault tolerance or error propagation properties of the exponential swap gate and whether they've been studied or not.
Yes, this is actually, I didn't, do I have a backup? I didn't include that slide here. So actually the errors happening during the beam splitter is very easily accounted because it preserves all sorts of parity and excitation numbers, so we can use the standard tracking protocols. The trouble is when things happen in between the two beam splitter operations, especially during the control phase shifts, because this is where the transmon gets entangled with one of the modes, and if a dephasing event occurs on the transmon, then that could actually scramble the state of the cavity that is entangled to. So Liang and Steve actually has a scheme. It's a little bit complicated. I don't know if we can implement it easily, but it is to use the higher levels of the transmon. So I think there is a science paper from Phil Reinold and Serge Rosenblum at Yale in 2019 that uses a similar technique. Basically, they do control phase shifts not with the GE eigenstates of the transmon, but they use the GF. So if the F had a jump, then you can detect it and maybe
F is just some higher.
Yeah, it's the third level.
Okay.
And we can actually also address the fourth level. So if you use the third level, you can account for a jump in the transmon. If you use the fourth level, there's actually some interesting tricks that Liang and Steve has to make it also detectable when it's a phase event. So it is possible, but at this point, I don't think anybody is actively pursuing that aspect yet.
Got it. Cool.
All right. I think that's probably, unless someone's got an urgent question, they're going to talk over the top of me. Great. So look, thanks again very much, Yvonne. That was a wonderful talk. Fantastic to have you join us and give your presentation. And I think anyone who feels like unmuting again, we might give you a proper clap.
Thank you. It's my pleasure. It's been fun. Thank you, everyone.